Welcome to the next video in the Mathematical Logic series, talking about Chapter 2, First Order Logic, and in this video, congruence relations. So let's start by defining a strong homomorphism. So a homomorphism is called strong if not only whenever a relation holds in the domain, then the corresponding element holds in the corresponding relation in the range. But in a strong homomorphism, there's at least some ability to kind of go back. So what that really means is that whenever you have the image of some element A, right? So this phi of vector A, right? And keep in mind, vector A is basically just the sort of like inputs to a relation, basically a bunch of elements from A. And then phi of A is just the vector of all of their images. Anyway, the details are in the book if that's necessary, but so this phi of A is like the image of some vector. And we're assuming that these elements hold in this relation in the range. And so we're saying that whenever that happens, then you can go back to the domain. Now, maybe the relation holds among the elements of the original vector A, but we don't require that full condition. Rather, all we require is that some element that also map to the same thing, right? So the sort of mental picture that you can have here is that you've got a vector A, you've got a vector B, they both run to the same phi of vector A, that is to say the same phi vector B, right? So this is the image that you have, and we're assuming that the relation holds on the image of the vector. And so we're saying that although we may see it as this and backtrack it to the vector A, we don't actually require that the relation in the domain structure hold on A, but just that it hold on some vector which also maps to phi of A, right? So it could be this other vector B, so long as the vector B maps to the same thing that A maps to. So this is the idea of a strong homomorphism. Now, to talk about a congruence relation, we are going to distinguish between two subtly different things, an equivalence relation and a congruence relation. Now, in a lot of other fields, we often talk about these two things as if they are the same thing, but here we're actually going to consider them as different. We will talk about an equivalence relation as the familiar idea, any relation that is reflexive, symmetric, transitive. And a congruence relation will be a special kind of equivalence relation. In particular, a congruence relation, and here we're talking about a congruence relation in a structure A, is one which, so to speak, respects all of the operations in the structure. What that means is, and this really only matters for the function symbols. So, right, this is a requirement only on the function symbols. And the requirement is that when two things are in the equivalence relation, then their images on every function in the structure are also equivalent. So that's like respecting the operations. So, right, some equivalence relations on the domain, just to try to imagine some contrast here about how this could fail, because it might seem like, what is this really saying? Could this ever not happen? Well, it can, right? You can find a way of taking the domain, cutting it into partitions. That's the same thing as an equivalence relation, is partitioning the domain. And you might partition the domain in such a way that an element from one cell of the partition and another cell of the same partition, the images on some operation send it to some two different cells. So that's what we are outlawing when we call something a congruence relation. So in effect, if you took any cell of the congruence relation and map any of the elements on the inside of it, they all must go to the same cell as their image. That's what we are requiring. Next, we're going to define the notion of the kernel of a homomorphism. Now, this really is going to be a fairly distinct, right? There is a relationship, but there is going to be a somewhat distinct idea of what the kernel of a homomorphism is in logic as contrasted with, say, abstract algebra. And so we are going to say that the kernel is an equivalence relation, not just a set, but an equivalence relation on the set, defined by two things are equivalent to each other if and only if they have the same image under the homomorphism. And it follows from that definition that this always is a congruence relation. And so that is the kernel of the homomorphism H from A to B. Now, as is common, once you have a homomorphism in abstract algebra, we know that one of the first things we want to do with a homomorphism is start talking about the quotient structure, whether that's the quotient group or ring or whatever. And so we're going to do a very similar thing here. We're going to talk about the quotient structure for a given homomorphism from one structure to another. Now, the book persistently uses this slash wavy equal sign even on elements, and that's something I'm not going to follow. I am just so used to writing a particular equivalence class, a cell in the partition, with this like bracket A, where A is some element of the set. So that's for a particular element, whereas when I talk about, you know, entire sets or even functions and relations, I'll go ahead and follow using this sort of quotient notation. But on particular elements and even on vectors of elements, I'm not going to follow the author in writing that with a slash wavy equal sign. I'm going to write it with the square brackets that I'm used to. So that is an explanation of the notation of the slash wavy equal sign, right? That is just the cell of the partition where A lives. It's a set of all things that are equivalent to A. And we will also use this slash wavy equal sign to talk about the set of all the cells. When I put a bracket on a vector, I really mean the vector of all the brackets. Okay, so we now want to sort of start trying to describe this, right? Like how we could actually get the quotient structure, right? So we haven't quite said what the quotient structure is because we haven't said what we're going to do with how we're going to interpret the extra logical symbols. And so that's what we have here, right? So we can define this quotient structure by saying that for any constant symbol in the language, it will be interpreted in the quotient structure by taking the denotation in the original structure and finding its equivalence class. Likewise, right, we have this definition of if you take the function symbol interpreted in the quotient structure, its argument must be an equivalence class. So we imagine any arbitrary equivalence class of a vector A. And what will it be? Well, you simply take the denotation of the function symbol in the original structure on the original vector A and find its equivalence class. And likewise, right, there's another statement for the relationship symbol. This is how we define the quotient structure, and we write it with this script A slash wavy equal sign.